All right, good afternoon, everybody. Welcome to lecture 26. Still talking about open channel flow and hydraulic jumps today. And we have a nice example behind me of a hydraulic jump, which is similar to the one that I've asked you to do this week for extra credit in your kitchen sink or bathroom sink. Super easy. If you have a high enough flow rate, you can just turn the faucet on and you'll see this huge circular change in the depth of the fluid at a certain radius out. So it's really interesting phenomenon. All right, let's turn over to the annotator and get started. Okay. All right, so here we go. Today we're talking about, continuing to talk about open channel flow. We're going to talk about really often used equations, the Manning equation. And we'll talk about the phenomenon of hydraulic jump, as you can see behind me. Let's start by talking about some of the basic concepts in uniform open channel flow. So if we have uniform depth and velocity along the channel, then we can write that dy, the depth of the fluid with dx, is zero, right? But we can have changes in elevation. So just something to keep in mind in case you might think maybe intuitively, oh, well, if the elevation is changing, the depth won't change. That's not always the case. All right, let's look at this example. We're looking at the channel flow. It's flowing from left to right here with volumetric flow rate Q. And then we're just looking at this section, AA, rotating it around 90 degrees. And then we're seeing a cross section of this channel flow, right? So I think I mentioned that last time, but a really important quantity in channel flow is the hydraulic radius, and its definition is the cross-sectional area of the flow, so what you see shaded here in blue, divided by the wetted perimeter, right? So not necessarily the perimeter of the channel itself, but just including the depth that the water goes to. So if this channel, for example, were much higher, here, but the water only went up to this level, we would only include the wetted perimeter that's up to the height where the water goes. All right. So another note that's really important to understand about what we're assuming when we deal with open channel flows is that although in reality our velocity distributions in our channels and our shear stress distributions are not uniform, we make the assumption that they are uniform because it simplifies the analysis a lot, right? So here's a typical flow, cross-section of a flow in a rectangular channel, right? And your lines of constant velocity might be something like this. So if you were to take a slice, you might see a velocity profile like this here, right? Like sort of semi-parabolic, but then getting cut off at the top, right? Well, we just come along and we say, okay, we're going to take the average value of this velocity profile, use that, and just make the assumption that the velocity profile is uniform. It's close enough, right? Here's a cross-section through a pipe, and you get a very similar profile. And again, of course, we just take the mean velocity value in these situations and use that. And then here's an example of shear stress, wall shear stress, right? So the actual wall shear stress distributions might look something like this with these curves going to zero at the corners, but then we make the assumption that it's just uniform on each face, right? So as you see with these dashed lines here. All right, so let's talk about the Manning equation. Probably if you were, to be asked as a civil engineer, maybe my civil engineers can vouch for this, what's the fundamental equation of civil engineering when it comes to fluid flows, right, to channel flows? So you might say the Manning equation. So if we look at a channel flow, in the picture here on the right, we see the channel has a slight slope, so the flow is slightly downhill, and that's described by the angle theta. We've got a number, we're taking a control volume analysis approach, so we're just taking a cubic rectangular control volume here. And we've got our control surface. We know that the shear stress is 0 at the top because there's no viscosity, or there's negligible viscosity between air and water. But we do have, in principle, a pressure force at the upstream face at section 1, and a pressure force pointing in, as always, and the downstream location at section 2. We've got the two different depths of water Y. We've got the fluid weight, and then we've got shear stress at the wall, which always acts opposite to the flow direction, right? It always acts to slow the flow because of friction. All right, if we assume now steady uniform flow, and we sum forces along the flow direction in the x direction, just writing down our expression that we've derived all the way back in chapter 3 and 5 for the flux of linear momentum through the control surface. Right? And that's going to be equal to the forces acting on the control volume in the x direction. All right, so this is what we have. And since the flow is steady, it's not accelerating, right? It's just moving in a constant velocity. We know that the sum of the forces in the x direction is equal to 0, right? However, we've got uniform flow. If you remember from what we talked about with uniform flow, that means we've got a uniform depth, right? So that means that y1 is equal to y2, which implies that, let's call it F1 and F2, which implies that F1 equals F2. And you're going to see this assumption all the time in open channel flow. It's the assumption that the pressure force acting on the control surface is a hydrostatic pressure force. And then with uniform channel flow, because the depth is the same, that hydrostatic pressure force is going to be the same across both these faces at sections 1 and 2. So those pressure forces cancel. Right? So we are now going to rearrange and solve for tau wall, setting F1 and F2 equal to 0. So if we rewrite this, we get that sine of theta is just the slope of the bottom wall. We just call it the bottom slope. So the slope of the bottom wall of the channel. Here, we've also used small angle approximation, since that slope is typically much less than 1. All right. So rearranging now, we've got tau wall is equal to gamma. We're just rewriting the weight in terms of gamma. A, L, the length of this section, the length of the control volume. S naught, that bottom slope, over P, the perimeter, times L again, which when we cancel, it's just gamma, the hydraulic radius, times S naught. Right? And I'll just rewrite tau wall over here on the right-hand side so that I can box this equation. This is 1013. Right? So now we have an equation which is an expression for the wall shear stress in terms of the fluid you're dealing with. Usually it's water, so gamma, the hydraulic radius, and the bottom slope. So this applies again to steady uniform flow. Okay. Now we use this all the time together with the Manning equation. I'm not going to derive the Manning equation here because it's not derived from first principles. It was found empirically from taking many hundreds, if not thousands of measurements on different channel flows. And so I'm just going to write down the velocity form and the volumetric flow rate form of the Manning equation. All right, so Manning equation tells us that the velocity, that uniform velocity in the open channel, depends on the hydraulic radius raised to the 2/3 power, the bottom slope raised to the 1/3 power, and then we've got these two constants. The top one, kappa, just takes care of units, and so that's a little funny. It's 1 if you're using SI units, but it's a different value if you're using British gravitational units. So because the Manning equation is an old historic equation, they were a little bit sloppy about units, right? So we have to do this. So sorry, let me just write that clearly. It's 1.49 if you're using BG units. Okay. And then let me write down the flow rate version of the equation. And this is equation 1017 in the book. And then N is this Manning coefficient, and that's a lookup table number, right? So you go to the table, it's table 10.1 in the textbook. If it tells you it's, rough concrete, it depends on the material and the roughness. Whatever material you're given in the problem, you look up the Manning coefficient and use that in your equation. All right. And then down here on the lower right, this is just an illustration that the pressure distribution on the sides of the channel are going to be equal, as well as at the front and the back at sections 1 and 2. And that's because of symmetry. Okay, so here's this Manning coefficient N. So it's in your textbook as table 10.1, and of course you'll be able to print a copy of this for the final midterm in the course. And you can see it's just, for different types of channels, natural floodplains, excavated earth. Probably the highest ones you have is down here for floodplains, so for trees it goes up to 0.1. And then the lowest values you have are over here for artificially lined channels. For glass, about 0.01, a full order of magnitude lower than for the natural tree flow situation. All right, so let's just jump right into some examples. So here we've got a 2-meter diameter pipe made of finished concrete, and it's got a very slight slope, 1 meter of elevation change per 1,000 meters of pipe length. What's the flow rate when the pipe is half full, right? So here we want to use the flow rate version of the Manning equation. But let's just take a look at the situation we're dealing with. So we've got a circular pipe, it's exactly half full. So our area, let me actually do the area in red. So our area is this half circle area, and then the perimeter as well just goes up around half the circle. And our diameter is 2 meters. Okay, so now we're going to use the 1017 version of the equation, the Manning equation. And right, Q is equal to, first we'll just write the fundamental definition of the volumetric flow rate, right? The cross-sectional area times the mean velocity. But also by equation 1017, it's equal to kappa over N, cross-sectional area A, hydraulic radius to the 2/3, slope to the 1/2. So here, for this problem, we're using SI units. So that tells us that kappa is equal to just 1. The slope, S naught, the bottom slope is 1 meter over 1,000 meters, which gives us 0.001 unitlets. Our hydraulic radius is equal to A over P. So that is 1/2 times pi over 4 d squared over pi d over 2, right? Perimeter of the circle divided by 2. So this turns out to be just d by 4. Our diameter is 2 meters, so this is 1/2 meter. And then finally, we have to look up the value for the Manning coefficient N from table 10.1. For finished concrete, which is exactly how it's worded in the table. We find that N is 0.012. All right, so now we just go back, plug all of these values into the Manning equation. Nice thing about open channel flow, there's not a lot of guesswork involved in solving these types of problems. It's usually just, look up the type of material, calculate the cross-sectional area, calculate the hydraulic radius, and then plug in the equation. So we've got 0.012 times 1.57 meters squared. Sorry, that's the area, by the way. So if you write out what this is, it is 1.57 meters squared, if you calculate that out, times d over 4 to the 2/3, times our bottom slope, S naught, to the 1/2 power. And this gives us 2.61 meters cubed per second as the flow rate through this concrete pipe, right? So you can imagine this, on a construction site, something like that. You're laying water pipes for a city. So if you have just the diameter of the pipe and the slope, and the slope is relatively small, you can make a reasonable assumption that you're dealing with uniform channel flow under most conditions and calculate the flow rate. We could have also calculated the velocity, that uniform value for the velocity. All right, any questions on this example? All right, I'll move on, but as you know, you can jump in at any time. Okay, so now similar example. All right, do you have a question? When does the slope approximation fail? Basically, when the small angle approximation fails. So when you can no longer say that sine of theta, so what's theta again? Right, going back to this figure, theta is your slope, basically. It's, you know, it's a measure of your slope. So when you can no longer say that sine of theta is approximately equal to tan of theta is approximately equal to theta, then it fails. And so rule of thumb as engineers, we usually say that's, you know, a theta of 10 degrees, something like that, right? All right, second example. And as I noted on Monday, I'm now including, you know, by your request, I'm now including in the lectures, instead of working through example problems that are already in the text of the chapter, because those already are worked out and you already know the solution, I'm working through problems that are from the back of the chapter where you don't already have the solutions available. And that's a great idea. So thank you for pointing that out. This is problem 1056 in the back of the book. And the last one that we looked at was 1036. So let me actually note that. Okay, so here we have a rectangular unfinished concrete channel of 28-foot width, and it's laid on a slope of 8 feet per mile. And now we're given the flow rate. It's 400 cubic feet per second. Now we want to determine the flow depth and the Froude number. We talked about the Froude number last time. The Froude number is something that we can calculate given the velocity for our channel flow, the constant of gravity, and the depth of our channel flow. So if you remember, our main result from last time was this equation. Doesn't like it when I write up there, so let me write here. Our main result from last time was that if you throw a pebble into a pond and you get those waves on the surface, or anything else that's going to cause waves on the surface of the channel flow, that you can actually find out, calculate to a reasonable degree of accuracy what the wave speed is just from the constant due to gravity and the depth of the body of water, right? Y. So that was the main result we talked about last time. We talked about why ocean waves hitting the shore at an angle tend to straighten out right before they break using that equation. Now we're going to use it to calculate the Froude number. Okay, so here we're going to use the Manning equation again, the same one that we used in the last example, but now we already know Q. We're trying to calculate some other things. First, let's just draw a sketch of the type of flow situation we have. So 28 feet wide. Some depth. And of course, we always remember that these flows are open to the atmosphere, right? So we know that it's atmospheric pressure at the top. Okay, so going back to our equation, the Manning equation, this time we're dealing with British gravitational units, so we need to use a value of kappa of 1.49 instead of 1. And we'll put this over n for now. We've got our cross-sectional area, our hydraulic radius to the 2/3 power, and our slope to 1/2 power. So just plugging in all the numbers that we have available. We've been given that the flow rate is 400 cubic feet per second. Let's come over to the right and calculate the other items that we need. Okay, so our bottom slope, we're given everything we need to calculate that. It's 8 feet per mile, but 1 mile is 5,280 feet. So our bottom slope is 2 zeros and then 15, 15. We look at table 10.1 again, this time for unfinished concrete. And we find that n is 0.014, not that different from the value we had in the last example, right? For finished concrete, our value for n was 0.012, which is 0.014. Our A is equal to 28 times y. We don't know the depth yet. And our perimeter, our wetted perimeter, is going to be 2 times y on the edges plus 28 on the bottom surface, right? So we do have to keep this in terms of our unknown y first, and y is going to be the first thing that we're solving for. Similarly, our hydraulic diameter is just A over P, right? So it's going to be 28y over 2y plus 28. So now we're going to go back over to our Manning equation and plug all this in. We'll simplify this. And we get 0.458 times y plus 14 minus y to the 5 halves equals 0, which gives us that y is equal to 2.23 feet. And that's the first thing that we've been asked for. Right? What's the depth of this flow? So we didn't know it, but we know we knew we had an equation that was given in terms of the depth, sort of implicitly through the area and the hydraulic radius, right? Now, maybe you could say, well, which version of the Manning equation do we use? The one for V or the one for Q? Well, you know, it's just a little simpler to use the one for Q here because we're given that the flow rate is 400 cubic feet per second. All right, now we want to calculate the Froude number. If you remember, the Froude number tells you how to categorize your channel flow in terms of criticality. In other words, is your channel flow speed faster than a wave speed would be at the surface or slower? Normally, our normal situation is that the wave speed is much faster, right? So that's why you could have a slow current in your pond and you throw in your stone and you still see what looks like mostly circular waves radiating outwards because that wave speed is much faster than whatever current you have at the bottom of, you know, your slowly meandering semi-pond that's coming off from a river, something like that, right? But when that's not the case, when our Froude number is elevated, then we can get really interesting stuff happening like hydraulic dumps. So I'll work through the Froude number calculation here and then I'll ask you if hydraulic jump is possible. So let's go ahead and calculate the value for our uniform velocity from the volumetric flow rate and the cross-sectional area. So our velocity is 6.41 feet per second. So now the crude number is, its most basic definition is the uniform velocity of the flow in the channel, V, over the wave speed, right? But we almost always use this equation that we derived last time, which is the wave speed is just the square root of the gravitational constant G times the depth of the channel, right? So we'll do that here, 6.41 feet per second over 32.2 feet per second squared times 2.23 feet to the 1/2. And we get that our Froude number is 0.756. So a question for you, is this subcritical or supercritical? Can we ever have a hydraulic jump in this flow? So it turns out, okay, subcritical, thank you, Leah. Yes, it's subcritical, it's less than 1. That means that we can never have a hydraulic jump, right? So a hydraulic jump is something that happens when the flow in the channel catches up to the wave speed, and then you can get basically stacking of depths. You get a bunch of waves stacked at one location because the wave and the channel flow are at the same rate, right? So fluid particles in the wave and in the channel below them are moving in the same location. That's when you can get a hydraulic jump. So yeah, this indeed is subcritical flow because it's less than 1. All right, any questions about this example? All right, let's move on and talk about hydraulic jumps. So a hydraulic jump is what happens when you have a flow and suddenly there's a almost discontinuous, almost step function change in the depth of the flow, right? It increases very drastically in height over a very short extent, right? Flow direction extent, right? So, and this happens in steady flows. It's not because, someone sent a shock from upstream to down, although you could see something that looked like this because of some unsteady phenomenon. But hydraulic jumps are a steady phenomenon, right? So you've got a steady flow, and at some point, you've just got the height of the fluid increasing. So you can see it in the example behind me for flow from a faucet into a sink. And you can see it here in this example of a channel flow, and you can see it in the sketch here. And you can think of the reason for this phenomenon happening by thinking of the example of you're given a situation where you need to quickly decelerate the flow speed. So let's say, for example, that this flow here is going to meet a wall downstream, and it has to come to 0 at the wall, or it has to come to a very low flow speed at the wall, right? And here, because the cross upstream at section 1, because the cross-sectional area of the flow is so much smaller, you've got a much higher velocity than you do here at section 2, right? So by taking this jump in height, it allows the flow to decelerate, right? And so it brings the flow speed down. Obviously the flow rate is the same, but it brings the flow speed down quickly. And you also get a little bit of a loss of energy because of recirculation that happens right at the jump, and you get actually really high viscous losses there, or you can. You don't always, but you can. All right, so in this case, we assume that dy dx is on the order of 1, right? So the height goes from y1 to y2 over the same x extent as around approximately as y2 minus y1. To analyze this and come up with an equation that describes the hydraulic jump, we are going to make the assumption that the flow at the upstream and downstream sections, not at the jump itself, but on either end of it, is uniform. And we're going to ignore viscous effects for the analysis. All right, so looking at our control volume that we've drawn, we're going to write down the following equation, just like we did a couple slides ago. So F1 minus F2 is equal to rho Q V2 minus V1. That's the flux of linear momentum through the control surface, is equal to rho, just rewriting this, V1, Y1, V, V2 minus V1. Just rewriting Q in terms of the upstream cross-sectional area and uniform velocity. All right, and then rewriting the pressure, so these forces F1 and F2 are the pressure on sections 1 and sections 2, right? And we're making the assumption that we do all the time for channel flow. And that assumption is that because it's uniform flow, there's no acceleration, and because it's open to the atmosphere, the pressure across these sections is the hydrostatic pressure, right? So rewriting the pressure in terms of the hydrostatic pressure, we get this. So just to say what we've done, all right. So what we've done going from this equation to this one here is just rewrite F1 and F2, those pressure forces, in terms of the depth squared using this expression here, right? Just rewriting them as hydrostatic forces. And we're going to relabel that as equation 1. Now, interestingly, in this case for a hydraulic jump, of course, the two pressures at sections 1 and 2 don't cancel like they do for a uniform flow of uniform depth, right? In both cases, we're assuming that the pressure on the faces of the control surface at sections 1 and 2 are due to hydrostatic pressure. But in the previous example, when we derived the Manning equation, we had the same depth on both ends of the control volume. Here we don't, right? Y1 is much less than, or it's less than Y2, and so we have a difference in those pressure forces, and so they stay in the equation, they don't cancel. All right, conservation of mass, that was conservation of linear momentum. Conservation of mass gives us the following: Y1, B, V1, where B is the width of the channel, equals Y2, B, V2 equals Q. We'll call that equation 2. And then finally, the energy equation in terms of the form of 5.84 gives us that Y1, the depth upstream of the jump, plus V1 squared over 2G equals Y2 plus V2 squared over 2G plus a head loss. Call that equation 3. All right, we're going to combine equations 1 and 2. One's from the previous slide. It's the conservation of linear momentum. And we combine those to eliminate V2. Then we get y1 squared over 2 minus y2 squared over 2 equals v1 y1 over g times v1 y1 over y2 minus v1. Simplifying. Simplifying this all, we get y2 over y1 squared plus y2 over y1 minus 2 times the Froude number upstream, so it's got a subscript 1, squared equals 0. And then using the quadratic formula to solve and rejecting the negative answer, right? So we're solving for the variable here in this quadratic formula, and the variable is y2 over y1. We reject the negative answer from the quadratic formula because, you know, it doesn't make sense to have a negative height of fluid, right? Or depth of fluid. Okay, so we get the final form for our hydraulic jump equation, and it is that y2 over y1 is equal to 1/2, open parenthesis, minus 1 plus square root of 1 plus 8 Froude number upstream squared, square root. I'm going to box this in red because it's also a really important equation. So Manning equation, this equation, super important. So this is the hydraulic jump equation. You know, and you'll be asked different variations. You'll be given a flow situation. You'll be asked either to calculate one of the depths, y1 or y2, or the Froude number, you know, and you can go right to this equation. And let me just write down Froude number 1. All right, so that's our hydraulic jump equation. See how we're doing on time. Doing pretty well. Let me see if I can get through our final example before we wrap up for today. So let me just note that you can write the dimensionless head loss as well in terms of the equation we just derived. And this is equation 1027. You have this figure, which I did not write down what figure it is, but I'll mark that before I upload. So this figure tells you for a given Froude number, you've got two separate curves here. One gives you y2 over y1, different fluid depths before and after the jump. The other gives you the head loss, the dimensionless head loss. So for a given Froude number, you can just come to this chart and eyeball it and pick off either your dimensionless head loss for the hydraulic jump or your fluid depth ratio. And you can see there's no jump possible for Froude number less than 1, so this is blocked off here. All right, also table 10.2 gives you classification of, you know, for different Froude numbers, what kind of depth ratios you'll have. So Froude number less than 1, jumps impossible. So you see other interesting phenomenon, like if you have a Froude number between 2.5 and 4.5, you have an oscillating jump. Okay, example 3. It's our hydraulic jump example. So water flows upstream of a hydraulic jump with a depth of 0.5 meter and velocity 6 meters per second. What's the depth of the water downstream, right? So we want to pull out our y2 over y1 equation that we just derived. So we've got a situation like this. So we can go ahead and calculate the Froude number, the upstream Froude number. It's V1 square root of G Y1, and that's 6 meters per second. I'll fill this in before we hang up, but I want to make sure we have enough time. Turns out the Froude number is 2.71, right? So super critical, so definitely a hydraulic jump is possible. We go ahead and substitute this in on the right-hand side of our equation. And we get that the height ratio is 3.36. So we can then just do a little bit of algebra and get that the upstream water depth or water height is 1.168 meters. All right. Any questions on that example? I'll fill in these numbers while we're waiting. All right. So then let's go to the final slide. One thing that I didn't write down here that I want to mention before I forget is I had one student email me saying that he had a problem uploading his hydraulic jump photo to the extra credit assignment this week for week 11. So it's, the discussion is not a discussion this week. It's just, make a hydraulic jump in your sink if you can. If you have a high enough flow rate, upload a photo, whether it worked or not. And I had one student say he couldn't upload the photo. Has anybody else run into that issue? All right. Well, if you don't usually do the extra credit, you might want to do this one because it's really straightforward and simple. I want to give you guys a little break because of the election week. Many of us are distracted. Okay, and then finally, other note that I wanted to say is just that Hyungan is still grading. He was really busy the week after the exam because he had a midterm, and these questions are a little more complex than midterm one, so he is actually still grading. I'm making a couple of changes to the exam. I don't know if you noticed, but I threw out one of the questions, and I'm going to do a final review. Grades will be finalized soon, and I will send everybody an email when they are. So any questions for me? All right. Well, if there are no questions for me, we'll end 1 minute early today. Thank you guys for coming, and I hope you have a great rest of your week. And, try to engage in some self-care if you're obsessing about the election like I am. See you guys on Monday. Thank you.